You turn on ray tracing in a brand new game. The puddles look gorgeous. The lighting is chef's kiss. Then your frame rate nosedives into single digits. So you panic and Google how to fix ray tracing FPS. And suddenly, you're drowning in acronyms. DLSS, FSR, XeSS, frame generation, temporal upscaling. Everyone online is arguing and none of them agree. Here's the good news. These technologies are not nearly as confusing as the internet makes them seem. And by the end of this video, you'll know exactly what each one does. Ray tracing. You hear this term every single GPU launch. It's the feature that makes games look incredible and your frame rate weep. But understanding it makes everything else in this video click. Ray tracing is a rendering technique that simulates how light actually behaves in the real world. Traditional rendering uses something called rasterization. That method fakes lighting with clever shortcuts and pre-baked tricks. It's been doing this for decades, and honestly, it works great. Ray tracing takes a completely different approach. It traces the actual path of individual light rays as they bounce off surfaces, pass through glass, and scatter around a scene. Think of rasterization as painting a picture of a room from memory. Ray tracing is building the actual room and flipping the light switch. In a running game, ray tracing handles reflections, shadows, global illumination, and ambient occlusion. That wet road in Cyberpunk actually reflects the city above it. Shadows stretch and soften based on where the light source sits. Characters get soft, realistic lighting instead of looking like they're standing under a fluorescent office bulb. It's the technology that finally closes the gap between gameplay and pre-rendered cutscenes. Now the hardware side is where things get spicy. NVIDIA introduced dedicated RT cores with the RTX 2000 series back in 2018. Those cores handle ray tracing math separately from the regular graphics workload. AMD added hardware ray tracing support with RDNA 2 in their RX 6000 series. Intel brought it along with Arc, but here's the brutal truth. Ray tracing is outrageously demanding on your GPU. Turning it on can slash your frame rate by 40 to 60%. It's like strapping a boat trailer to a sports car. Still technically fast, but you feel every single pound. For gaming right now, you want at least an RTX 3060 Ti or RX 6700 XT level card to even consider it. Anything weaker and you're running a PowerPoint presentation with extra steps. The real move is pairing ray tracing with an upscaling technology, which is exactly what the rest of this video is about. The biggest myth is that ray tracing is all or nothing. Most modern games let you toggle individual effects separately. Turn on ray-traced reflections but keep shadows rasterized. Cherry-pick what actually looks good without giving your GPU a full meltdown. DLSS. This one confuses people way more than it should. It stands for Deep Learning Super Sampling, and it's basically NVIDIA's answer to ray tracing murdering your performance. If ray tracing takes your frames away, DLSS is the technology that hands them back. Here's what it actually does. Instead of rendering your game at full native resolution, the GPU renders at a lower internal resolution. Then NVIDIA's AI model takes that lower res image, analyzes motion vectors and temporal data, and reconstructs it into something that looks like the full resolution output. Sometimes it looks even better than native. It's like ordering a medium coffee and the barista secretly handing you a large. The key hardware here is tensor cores. Every RTX card has them. DLSS runs its neural network on those dedicated tensor cores, which means it barely touches the regular graphics pipeline. Your GPU renders fewer pixels. The AI fills in the gaps. Basically free performance. Well, almost free. DLSS has evolved dramatically since launch. Version 1.0 arrived with the RTX 2000 series, and it was rough, blurry, inconsistent, and each game needed its own AI training. DLSS 2.0 changed everything with a universal model that worked across all titles. The quality jump was massive. DLSS 3 launched with the RTX 4000 series and introduced frame generation. That's where the AI literally invents entire frames between the real rendered ones. Your GPU renders one frame, the AI creates the next. If you've tried it with ray tracing cranked up, drop your experience in the comments. DLSS 3.5 added ray reconstruction for cleaner ray-traced visuals, and DLSS 4 with the RTX 5000 series brought multi-frame generation, producing up to 3 AI-generated frames for every real one. The catch is exclusivity. DLSS only works on NVIDIA RTX GPUs. You need those tensor cores. Frame generation specifically requires an RTX 4000 series or newer. If you're on AMD or Intel, this party is not for you. Which is exactly why the next two technologies exist. One thing people consistently get wrong: DLSS is not fake resolution. The AI model is trained on massive datasets using NVIDIA's supercomputers. It's making intelligent visual predictions, not just stretching pixels. At quality mode, most people genuinely cannot tell it from native rendering. FSR, AMD's Fidelity FX Super Resolution, is the upscaling technology that works on basically everything. If DLSS is an exclusive VIP lounge, FSR is the open bar at a house party. Everyone is invited, no membership required. FSR does the same core job as DLSS. Render at a lower resolution. Upscale smart. Get more frames. The big difference is how it gets there. FSR 1.0 launched in mid-2021 using purely spatial upscaling. No AI involved. No temporal data. Just a really clever sharpening algorithm applied to a lower-res image. It was fast, and it was free. But the quality couldn't touch what DLSS 2.0 was doing. FSR 2.0 was the real turning point. AMD switched to temporal upscaling, which uses motion vectors and frame history to reconstruct detail. That was a massive quality jump. Suddenly FSR was getting genuinely close to DLSS in a lot of games. Not identical, but close enough that you wouldn't notice at a normal viewing distance. FSR 3.0 then added frame generation to match DLSS 3. Same concept. AI-generated intermediate frames for smoother gameplay. The biggest spec to understand with FSR is compatibility. It runs on virtually any modern GPU. NVIDIA cards, AMD cards, Intel Arc, even the Steam Deck. FSR doesn't need dedicated AI hardware. It runs on standard compute shaders that any recent GPU supports. That's its superpower. No brand lock-in, no generation requirement, just install and go. For choosing the right preset, quality mode is the sweet spot for most people. It gives the best balance of visual clarity and performance gain. Performance mode pushes the upscaling harder, and you will start noticing some softness. Ultra performance is reserved for 4K displays where you desperately need every frame you can squeeze out. FSR pairs especially well with ray tracing, since that's where the performance headroom really pays off. The common mistake is dismissing FSR as the worst DLSS. That was fair criticism in the FSR 1.0 days. Not anymore. FSR 2.0 and newer are genuinely competitive. In some titles, FSR actually holds up better during fast motion. The gap has narrowed dramatically, and since it's fully open source, developers can implement it more freely. If you're not on an RTX card, FSR is your best friend, and it's a great one. XeSS. Intel's XZ super sampling is the newest player in the upscaling game. It gets constantly overlooked, and that is a mistake. If DLSS is the established veteran and FSR is the crowd favorite, XeSS is the quiet transfer student who actually aced every test. XeSS does the same core job. Render at a lower resolution. Upscale intelligently. Get better performance. Intel launched it alongside the Arc Alchemist GPUs in late 2022. Like DLSS, it uses AI-based upscaling powered by dedicated matrix hardware. On Intel Arc GPUs, it runs on XMX cores. Think of those as Intel's equivalent of NVIDIA's Tensor cores. But here's what makes XeSS genuinely interesting. On non-Intel hardware, XeSS falls back to DP4A, a widely supported instruction set. So it actually works on NVIDIA and AMD cards too, not just Intel. The quality on Intel Arc hardware is legitimately impressive. XeSS at quality mode rivals DLSS in a solid number of titles. On non-Intel GPUs, using the DP4A path, quality dips slightly. It's like running a game on high settings versus ultra. You notice if you're pixel peeping side by side. In actual gameplay, it's basically the same experience. XeSS 2 arrived with Intel's Battlemage generation and added frame generation to the mix. Same idea as DLSS 3 and FSR 3. AI-generated frames between the real ones for smoother motion. Intel even open-sourced parts of the framework for developer flexibility. The main drawback right now is game support. XeSS is in far fewer titles than DLSS or FSR. But that's an adoption issue, not a quality issue. The technology itself genuinely holds up. For choosing, if you own an Intel Arc GPU, XeSS should be your first pick every time. It's optimized for your hardware and uses those dedicated AI cores. If you're on NVIDIA or AMD, you'll usually have DLSS or FSR as your primary option. But in games that support DLSS and not the others, it's a perfectly solid choice. The biggest myth about XeSS is that it doesn't matter because Intel GPUs aren't popular enough. The technology is competitive with both DLSS and FSR. Intel's discrete GPU lineup keeps getting better. As more developers adopt NVIDIA, it becomes harder to ignore. If you're still sleeping on Intel graphics, tell me why in the comments. So there it is. Ray tracing makes your games look absurdly good, but absolutely punishes your GPU in the process. DLSS uses NVIDIA's AI wizardry to claw that performance back. FSR does the same thing for everyone, with zero hardware lock-in. And XeSS proves Intel isn't just here to make processors. The technology is different across the board, but the goal is identical. Play beautiful games without your graphics card catching fire. What upscaler are you actually running right now? DLSS, FSR, XeSS, or are you raw-dogging native resolution like an absolute maniac? Let me know below. If this video helped clear things up, a like genuinely helps the channel more than you'd think. Next up, I'm covering every NVIDIA GPU generation from the very beginning. It's a wild ride through 3 decades of graphics. Click the video on screen right now.